Hello, everyone. I'm Ian Teixeira. I'm a PhD candidate here at University of Maryland College Park, and I'm going to be spending my dissertation today, which is called Quantum Codes, Transversal Gates, and Representation. All right, so the overview is I'm going to start with a little background, and then I'm going to talk about a typical problem, the problem of finding a quantum code with a particular set of transversal gates, and tell you basically how I originally approached the problem, establish that it was really hard, and then I'm going to get in the next section, getting it all for free. We're going to look at some deeper structure that we found, which allowed us to actually get an enormous amount of these codes, particular transversal gates, without having to solve an enormous system of conditions called the Delaplane condition. So it felt like we had this incredibly difficult problem where we had to simultaneously solve this enormous number of polynomials, the Delaplane conditions, and if we looked at it in the right way and used the right representation theory, we could kind of get it all for free. All the polynomials were immediately satisfied, which is very exciting. And then in part 4, we're going to look at some of the generalizations of that work. I kind of look back at how far we've come. Okay, part 1, background. Okay, error correction. So this is supposedly a talk about quantum error correction. And error correction exists in classical world too, classical computation. But it's especially important for quantum because, like a lot of folks in the audience, you have laptops and stuff, and your laptop probably doesn't use classical error correction because your hardware is sufficiently good that you don't really need it. Classical error correction is more for like cell phones or like sending things over noisy channels. But quantum is sort of inherently noisy, and even the equivalent of sort of like a quantum laptop, like a local quantum device, will still need quantum error correction. So it's really especially important to error correction for quantum stuff. So by extension, what I do is important. That's the message. All right. So a quantum code is a protected subspace. Qubit is just a vector in a two-dimensional complex vector space. And in its most naked form, a quantum code, it's just picking. So you have n physical qubits, which put you in a big Hilbert space, 2 to the n dimensional Hilbert space, and you pick some two-dimensional subspace, and that's your logical subspace. And you want to sort of pick it strategically so that errors on just one physical qubit won't corrupt your logical information in a irrecoverable way. And there are these things called the Delaplane conditions, which we'll talk about a lot. And they capture this idea of being able to sort of recover your information from an error. And in the particular case of encoding a single logical qubit into a bunch of physical qubits, you can sort of explicitly write down the Delaplane conditions in a basis, and you get this first set here that's sometimes called diagonal Delaplane conditions, and then you get this second condition here, which is sometimes called the diagonal condition, and we'll be hearing all this more here. Okay, so stabilizer codes. There's a bunch of math on this slide. It's not super important for what we're doing today. The name comes from the fact that the code space is the simultaneous +1 eigenspace of a bunch of commuting operators, or commuting matrices from some subgroup of the polygroup. So the code space is stabilized by all these polys. And the really important thing to know is that almost all known quantum codes are stabilizer codes. And so it's an enormous amount of nice structure that they have. There's lots of fault-tolerant techniques. It's sort of like there's this whole edifice built around them. And if you're not working with stabilizer code, it's kind of like you're wasting your time, basically. But this talk's all about working with non-stabilizer codes. So I'll sort of provide a counterpoint to that perspective. Yep. So part 2, this is about this problem of finding a quantum code with a particular group of transversal gates. And this is mostly material covered in this first PRL that I did with Eric, family of quantum codes with exotic transversal gates. It's sort of the story of writing that paper. So it all starts in a wonderful class, Quantum Error Correction and Fault Tolerance, taught in October 2021 by Professor Michael Gollins over there and also Professor Victor Albert. And they totally inspired me and Eric, and we got into all this stuff about quantum error correction. And some of the first things that I learned that kind of set me on this path are, I learned about transversal gaze. And a transversal gate is basically when you act on each physical qubit separately in a way that preserves the code space and maybe enacts some logical gate. So the classic one is like if you act on all 5 qubits, say with poly X, which is a gate that I showed up earlier, then maybe the effect that has on the code space is it sends logical 0, a logical 1, and logical 1, a logical 0, which means that this is implementing on the code space a logical X gate. So X is just this matrix that swaps the 0 and 1. And it's like a classic example of a transversal gate. And the reason that they're important is because we have to be able to do logical gates. Otherwise, our quantum arithmetic code is really just quantum storage. It's not actually doing quantum computing. The whole point of having a quantum computer is you want to be able to do things. You want to implement algorithms. So you have to be able to mess with your information and implement these logical gates. And the thing that's really nice about these transversal gates is that they implement some non-trivial logical gate, but they do it by acting on each physical qubit separately, so they don't spread errors. So these are sort of what are called naturally fault-tolerant logical gates. And that's the best. You want fault-tolerant logical gates. If we could do all our computation with fault-tolerant logical gates, then we would. But it turns out that that is impossible. So there's this famous, very nice formula called Ibist and nil, that the transversal gates can never be universal. At most, you get basically a finite number of them. And that was something I learned in this wonderful class taught by Michael and Victor. And I sort of was like, oh, that's really interesting. So for a single logical qubit, that means that your group of transversal gates has got to be some finite subgroup of SU2. And there's not that many finite subgroups of SU2. So I started kind of thinking about it. So I'm in the back of the class. I'm on like mass stack exchange, not paying attention, kind of like looking about the different subgroups of SU2. And it turns out this is a really, really old classification theorem going back to the 1800s. That they directly correspond to subgroups of 3 rotation groups, and there's very few of them. And the interesting ones are these 3 at the bottom. So there are some infinite families that I listed up top. The interesting one of these 3 at the bottom. So the 2T is tetrahedron, 2O is the octahedron, and 2I is the icosahedron. And there's this really nice exceptional symmetry that shows up in these 3 sort of special subgroups. And I said, okay, cool. I wonder what kind of codes have these as their transversal gate group. And it turns out, if you spend time on quantum computing stack exchange, like really spend a lot of time on stack exchange, you can find out that there's a famous code called the 513 code that actually is able to implement 2T transversally. And there's a very famous code called the Steam code that can implement 2O transversally. But no matter how hard you look on stack exchange, you will not find a code that implements 2I transversally. And so I said, well, that's kind of a shame. 2I is a famous example of kind of exceptional symmetry. And as a mathematician, you want to explore objects with exceptional symmetry. That's exciting. So I thought, well, it would be really great if we could find quantum arithmetic code that had 2I transversal gate group.
Yeah, I just have a question about notation. So when you write 513,
Yes.
it means there's a family of codes labeled 513, and this is a particular one?
So it turns out that all codes that encode 1 physical qubit into 5 logical qubits with distance 3 are equivalent. That's really uncommon. It's a very weird result for like the 90s. I think light frames proved it. And so it's not even just stabilizer codes, but it's actually, I love this fact. It's actually any code, even a non-stabilizer code. I love non-stabilizer code. So even if you try using non-stabilizer code, you can't do better than this particular stabilizer code that they'll dump in like Magic 5. 713 is very ambiguous notation. It just means it's a stabilizer code that encodes 1 logical qubit into 7 physical qubits with distance 3. There are a number of these. There happens to be up to equivalent. Only one of them is what's called a CSS code, which we could go into more later if you want. Yeah, color code, CSS code. There's like a well-known famous 7-qubit code, which I can talk about more later. Then, all right. So, yeah, I get to thinking about this, and I say, wouldn't it be cool to have a code that has 2i symmetry? And I sort of talking to Victor and Michael after class, and Michael's like, yeah, that seems really cool. You should look into it. And I like sort of look into it, but also like I'm busy because you know how life is. And also like just seems like a hard problem. And a rich big moment is many months later in May of 2022. Michael sends me an email and he says, I was just up at Princeton talking to Peter Sarnak. He has this crazy paper and it seems to use 2i in a way that seems very similar to kind of what you're talking about. You should look at the paper. So it turns out there's really a connection here. And say you want to get a nice universal gate set. Like I said, the transversal gates G can only be a most finite group. So you're never going to get a dense subgroup of SU2 from just transversal gates. You have to add something on top of your finite group of transversal gates to get a dense subgroup of SU2, which is what's called universality, is being dense in a unitary group. So you have to add something, and the name of the game is to pick that one other gate you're going to use in a way that you have to use that as little as possible. Because it's basically free almost to use these transversal gates because they don't spread errors. But the moment you use that non-transversal gate, all tau here, it starts causing you all kinds of problems. So you want to minimize the number of tau gates. They're sort of expensive in terms of fault tolerance. And it turns out that you can think about this problem in a way that's related to like quaternion algebras and all kinds of fancy math. And you can say there are these things called super golden gate sets. And the one that's common in the sort of the world of stable logic code, the world of regular quantum computing, is the Clifford gates plus this gate called T, which looks like 1, 0, 0, squeeze it to 5 over 8. That's like an 8-root unity. And it turns out that set has amazingly nice gate compilation properties. They're very efficient algorithms that exist for compiling a good approximation of an arbitrary gate using T plus Clifford. But what Sarnak found out was that 2i plus a particular strange gate called tau 60 has even better approximation properties. So it does this even faster. And that not only that, but it's the optimal. In the sense of his super golden gates, it is the optimal super golden gate set. So this is really cool because it shows that everyone else in the world is working with, Clifford plus T. But if you could do 2i plus tau 60, you might introduce a whole host of other problems, but at the very least, you would have this kind of optimality result. You could say, what I'm working with is even better in some sense than 2o plus T. So that was very intriguing. Okay, so at this point, me and Eric started to think, I just want to get Eric to think. Eric, you gotta help me with this. I have no idea how to start with this 2i code. I want to find a code that's 2i transversal. Here's kind of the setup. So the code having transversal gate group 2i is basically meaning it's a 2i sub-representation of this n tensor power, sort of the fundamental representation. So I'm looking inside of this big 2n dimensional representation. I'm looking for a nice 2-dimensional sub-representation that is close on the action of 2i. And so you can start by picking a particular logical representation, lambda, and kind of looking at the logical sub-representation, the lambda sub-representations of your fifth full space. And so that you want to use a lambda isotemic projector. That's kind of where we start. And since we want one logical qubit, then we want our code space to be transforming in a 2-dimensional irreducible representation, which is going to be either pi2 or pi2 bar. Because those are the two-dimensional representations of the binary cosecant group. And the one we start with is pi2, because that's sort of the natural representation. If you take 2i as an actual matrix group, then you just take the trace. That's sort of the natural one you get, whereas pi2 bar is basically applied outer automorphism, and you get a slightly different representation, which seems like it shouldn't matter. I mean, at the time, we didn't think it would matter which one we picked, but turns out later that. Okay, so this is sort of our general code finding procedure. Is we want to find this code space. We are going to pick the zero logical to be somewhere in the image of the isotypic projector because we want to transform in this logical representation of lambda. And what you can do is you can just look at, a basis for the isotypic subspace. So that will be all the eigenvectors bi. So p pi 2 is this isotypic projector onto the pi 2 isotypic subspace of the full Hilbert space. And the sum over the AI bi is basically all possible choices of 0 that will lead you to a lambda subspace. And that's a fair number. And in fact, the number that you get is really just the number of AIs, the number of coefficients that you're working with is just whatever the rank of this isotypic projector is. And once you pick the 0, logical 0, then because it's irreducible, you just act on the group G or the group algebra or however you want to say it, and you basically generate this two-dimensional subspace. And so it's just about picking the logical 0, but there's a lot of choices for logical 0. And if you just take kind of arbitrary AI, just kind of randomly picks up variables, the distance will be 1. I mean, it won't do anything. It'll just be a representation that's sitting there and not correcting any errors. So it's totally useless. So you have to think, I need this to not just be a representation. So it's not just a problem in representation theory, because then it'd be easy. I need it to also satisfy all these Newell-Flamm conditions that will give it high distance. That's where it becomes this quantum object, this useful object that corrects the errors. It is when it satisfies the Newell-Flamm condition. And there's a lot of these. There's a lot of these Newell-Flamm conditions. If you want to have distance D, then you have basically 2 is for the diagonal plus off diagonal. That's where the 2 comes from. 3 to the I, it's basically the 3 Pauli matrices. So this is X, Y, and Z. They're basically a basis for the Lie algebra brackets U2. And the general idea here is that the Lie algebra represents the sort of non-trivial errors. So you could also have just the identity matrix, but that doesn't do anything. That's not really an So the 3 is for the Pauli gates of I, and then you could put them in a bunch of different locations. So there's just some big number. And ultimately, you want to find a representation that satisfies this big number of conditions, which seems hard. In fact, it's hard. We were trying to simplify the search at this point by sort of using some of the nice structure of stabilizer codes, because at this point we're thinking everything's stabilizer code. We're going to find some stabilizer code that's 2i transversal. It'll be a cool stabilizer code, but it'll be a stabilizer code. At some point in November, I'm again on Stack Exchange, asking questions, learning things about the Clifford hierarchy, and I realize that everything is significantly different than I thought it was, because it turns out that you can never implement 2i transversally with a stabilizer code. It's impossible. So there's some very nice work about sort of disjointness. It's like a PRX by, I can't remember all the authors, where they show that for any stabilizer code, all the transversal gates will be in something called the Clifford hierarchy. And then there's some other nice structure results on the Clifford hierarchy, which show that any gate in the Clifford hierarchy is basically confined over Q adjoin, zeta 4, zeta 8, zeta 16. So these iterated, roots of 2 to the R roots of unity. And 2i, kind of the whole point of the character table is there's all these root 5s every full ratios everywhere. And it's like a simple algebraic number theory fact that you can't get a root 5 out of a bunch of, 2 to the R roots of unity. It's not going to work. So it is probably impossible for this gate to be in the Clifford hierarchy. We call gates around the Clifford hierarchy exotic, and therefore there's no possible way to become a stabilizer code that implements 2i transversally. So this was kind of like a real shocker at the time, and I kind of called Eric and was like, I don't know, we might have to give up all hope and burn the ships. There's no way to do this with stabilizer codes. And Eric, to his credit, had a really positive spin on it and was like, this is going to be great. This is going to be great because it'll mean that when we find this thing, it's going to be so different from anything anyone else has ever done because it's not a stabilizer code. So it's going to be 10 times as good now. So he really kept the sort of morale high. And you're done. All right. So at the time, it just made things feel even harder. We're getting into winter. We've been doing this for 6-8 months. We no longer have the structure of stabilized codes to rely on to simplify the search. So we're just kind of out there in the void, looking for something. We don't even know if it exists. And we basically need to be solving an extremely large number of these conditions, and calling them conditions and no-farm conditions simultaneously, and I'm doing it a large number of variables. And it's just a computationally intractable task. So it feels kind of impossible. But we keep our chins up and we sort of try and do our best. We think about, well, we don't have stabilizer codes anymore, but there's other structure that a lot of codes have. And so we put in some simplifying assumptions here. Say that a zero vector, we want to choose it to be a +1 eigenvector of z tensor n, and then we relate the logical 1 and logical 0 by this. This is this x tensor n. So this is like x tensor 5 over here, which is transversal x for the 513 code. But it's also true that x tensor 7 is transversal x for the 713 code. It's a very common structure that's common to a lot of codes. So we figured, we may not get a stabilizer code, but maybe there'll be at least some similarities to these codes that we already know and love. And also, it's true that for all these stabilizer codes, the coefficients are real numbers. Very strange. This happened in quantum, where the nice objects just kind of have real coefficients at the end of the day anyway, even though you're supposed to use complex numbers for quantum. And so this is another assumption that seems reasonable. The code words for 513 and 713, they're real. The code projectors are real valued. So we put in these assumptions, and that basically tells us that the nil Laflamme conditions for all the weight 2 errors are automatically satisfied if these assumptions are met. And that's a big win, because there's not that many weight 1 errors. Weight 1 errors are like x on 1 qubit or y on 1 qubit. But once you start having weight 2 errors, then things get nasty, because you can say have x on a qubit, and then there's all these ways of n shoot 2. And so it just grows much faster. So to take all of the weight 2 errors and immediately have them satisfied just based on some pretty innocuous seeming assumptions felt pretty encouraging. And it could be a little better, but it's still a pretty big haystack. Well, lucky for me, I have an Eric Kabishta, and he kind of got in there with the Mathematica code, and one day called me out and said, "You're not going to believe this. I'm a miracle worker." I mean, you never said it all. I'd say it's a miracle worker. Using this numerical search, I found a code. And this was almost 9-10 months into looking for the code. So at this point, we were really kind of thinking about giving up. I had a good talk with Mike the month before, where he was like, well, Ian, you could always write a non-result paper where you're like, it's really hard to find 2i principles to salvage something, which is, that's still advice at the time. But it turned out we didn't have to write a non-result paper because we got a result. So this is very, very exciting. This happened, I think, the first Monday of spring break that year. And Eric found it using Zaratan. Unfortunately, all of the code conditions were numerical. It's I hate, because I like algebra, and anyone would hate, because you don't really know it's satisfying your conditions. Just know it's satisfying your conditions up to 10 to the negative 12, which is so annoying. And writing it down looks so ugly. So it was good, but not as satisfying as it could have been. But then there was another miracle, because we sort of went back to the drawing board a little bit. You say, okay, we've been searching for the logical rep pi2 this whole time. Basically looking for pi2 sub-representations of pi2 tensor n. So this is an n-qubit Hilbert space. The action 2i on an n-qubit Hilbert space is going to be pi2 tensor n, and we're looking for pi2 sub-representations of that. And that was originally our approach. But we're just looking for a logical qubit, so why not look for subspaces that transform in pi2 bar? That's also a two-dimensional representation of 2i. And turns out that when you do that, you can find this in less qubits. So there is a copy of pi2 bar in 7 qubits. So 7, that's less than 11, that seems good. But the much, much better news is not only do you find it in less qubits, but the actual structure of the code, the actual code words, they show up and they're these beautiful algebraic numbers. You can just use find instance in Mathematica, and it's a small enough problem that it'll just spit out square root 15 and all this stuff. So this feels really good, because we can check this on the nose. We know we have an actual honest-to-gosh quantum error correcting code with distance 3 that implements 2i transversally. And that feels like something we can like really be excited about and really be proud of and like write up a paper and just get our stuff out there. So yes, this is a 7 qubit. So this is 7 physical qubits implemented encodes 1 logical qubit and distance 3. So as we're in the process of writing up this paper, like a couple months later, the June, we're in some office, I think on the 2nd floor down there, and we were looking at 9 qubits. We said, okay, we already found 7 qubits. Like, what can we do with 9 qubits? Like higher numbers. And Eric's found like all these different 9 qubit pi2 barcodes. And I'm looking at the coefficients, and they're just kind of random numbers. It seems like it seems kind of strange. And that beautiful 7 qubit code has these gorgeous like algebraic coefficients. The pi bits look random now. What's going on with 9 qubits? And I kind of take a look at it. I'm like, you know what? If they're just like look random, then maybe we're basically just picking points randomly from some bigger space of solutions. And so maybe like this whole pi2 bar isotypic subspace, actually everything is a solution. Like any pi2 bar subspace is actually a distance 3 code, which seems insane because we've been working so hard, optimizing so hard for so long, trying to find that one little needle in the haystack. But I'm like, what if the whole haystack is all codes? And so I'm like, what if we try sandwiching just an arbitrary any error in between the entire isotypic projector instead of working with specific code words? And sure enough, it just vanishes. You could just put the entire isotypic projector there and just it vanishes for everything. So you know that you're getting these nil Flamel conditions satisfied. In fact, not generally, you're getting them satisfying for just every weight 1 error, every weight 2 error. And this is like very exciting. There's definitely some piece of structure.
Sorry, you said weight 2? Also, here just said weight 1.
Oh, so for the weight 2, at the time, we're assuming the real code words thing. We're assuming this thing with like real code words on X is exactly code result. So then we get the weight 2 from that. It turns out later that weight 2 you actually do get for free. But at the time, we were still working with this real code word assumption. So it wasn't sort of immediately obvious. And okay. So this is part 3. Free codes as in free beer and free speech. This is an actual line from our first archived version of the safer quantum codes from twisted unitary T groups, which we originally called 3 quantum codes for twisted unitary T groups because we were so excited that we were having this moment. We were working so hard to optimize and drag these codes out using like numerical searches and all this nonsense. And finally, we felt like we had a general structure, this deeper structure over certain representations. We like everything, the whole haystack is all needles, right? And so this felt really exciting. The reviewers did not let us keep this claim of free because that's like, they're not really free. Like you guys doing all the complicated representation, dude. But in our hearts, we really felt that they were free codes. And then that captures how excited about them we were. You can still look at version 1 of the archive and it still says this. Okay. So this is kind of the deeper theory. The theory that we eventually cooked up connects the quantum codes we found with T designs, unitary T designs. It was something we were thinking about a lot at the time because the Clifford group is a unitary 3 design for any number of qubits. The binary icosahedral group is actually a unitary 5 design. In fact, it's the only 5 design that's possible. That's also a finite group. And so this is definitely something that was sort of percolating in our mind. So let me define for you what a unitary T group is. Okay, so a T design is a finite approximating set for something. So on the right-hand side here, you have basically, this is an R measure, you're integrating with the entire unitary group. And that's like hard because you're performing a big integral. It'd be nice if you could do this, approximate this with just a finite sum. That's kind of the idea of designs. We're kind of representation theory-ish, so we do everything in terms of representations. Normally, this f of g is just g, f star of g is just g star. Again, over here, f of g is just g, f star of g is just g star. So these are just sort of like polynomials in g and g star. T is sort of the degree of the polynomial. And a T design, the idea is that you can approximate all polynomials of degree up to T using just a finite sum. And that's sort of the idea. And the notation here is that F is a representation of UQ, G is a finite subgroup of UQ, and so F down is just branching this representation of UQ to the corresponding representation of G. Now, one thing that's nice is when we take F tensor F star, that's basically the conjugation action on the operators. So if F is just the standard, if we're doing U2, right? Then F is just like the standard representation of U2 acting on C2. And then, so let's see. Call this like bold 2, I guess. And then bold on a chunk. I don't know, like bold 2, right? There's a unique irreducible representation of SU2. You can kind of work with SU2 all the time because it's quantum mechanics, so global phases don't matter. So PU2, SU2, U2, it's sort of all one and the same. So it's a unique irreducible representation of dimension 2 of SU2. And if you do SU2 tensor to star, then you basically get, a copy of the agile representation plus just a copy of like the trivial representation. And this is true for any Q. If you have SUQ, and then you do Q bar tensor Q star, then you get an adjoint representation plus just a trivial representation. And remember that this is really just separating out the identity matrix from all the non-identity errors. So these are sort of all the weight 1 errors are transferred from the adjoint representation, all the weight 0, which is just the identity. The identity is over here. And so we can think of powers of the adjoint representation as really representing, so the first power of the adjoint representation is weight 1 errors. And the second power of the adjoint representation is weight 2 errors. So by analyzing things about the T tensor power of the adjoint representation, we've learned things about the action of G on the errors on this code. So the way you can kind of walk through this is that, see, F tensor F star is 1 plus adjoint. Now you break 1 plus adjoint tensor T into irreducibles. So basically, R are all the irreducibles that show up at least once in adjoint tensor T. And so you can just sort of analyze this based on irreducibles, and you say, we have this equality over line 3, if and only if for each irreducible that's present, we also have this equality. And so R is an irreducible representation with Q. R down is just branching that irreducible representation of UQ down to a representation of G. And now we can think of these things as isotypic projectors. So this could bring us back to isotypic projectors. So we can sort of sneak in a copy of 1 and imagine this to be isotypic projector of the trivial representation. So that means that it'll vanish unless, of course, R is equal to 1. So whenever R is not equal to 1, then this should vanish. In order for this to be true, we need the left-hand side to vanish because we know that if R is an irreducible representation of UQ, and then we project onto the trivial representation of UQ, this will vanish. And so ultimately, to have a unitary T group, we just need, as a representation of G, we need R down to have a trivial isotypic projector when we project onto the trivial representation, which just means that interfacting character is E0. So this is like kind of some fancy footwork with representation theory. We can also a generalization of this, where lambda is some irreducible representation. And now I'm going to take a weighted design. So instead of taking a uniform sum over the finitely many elements of the group, we're weighting each element in the group by a character value squared. And this really is a weighted design in the sense that this is a probability distribution, because the sum of all the lambda G squared over size of G adds up to 1. That's just like the inner product of lambda with lambda. Lambda is irreducible, so that's going to be 1. So we can go through all the same steps, but now there's this sneaky lambda G squared on the left-hand side. And so we're still projecting onto the trivial representation here, basically. We're thinking of this as the isotypic projector from RGF, the trivial representation. But over on the left-hand side, we're thinking of this as an isotypic projector from R down onto lambda G squared. So it's an isotypic projector, but it's now onto lambda G squared. And so we're tracking that, and we look at that with the inner product of lambda star lambda with R down. And this is just kind of a bunch of elaborate definitions. What does it actually have to do with quantum error correction? And that is a good question. And basically, here's the argument for why this has some implication for errors naturally being satisfied. So let's say you have a code. Your code space, let's call it C. C is transforming the irreducible representation lambda. And now let's also imagine you have a bunch of errors and they're transforming in some representation. We'll call it curly E, or no, I guess we're calling this all. We're calling this E, I guess we'll call the vector space E. R will be the representation. So let's say take a nice tensor product and we're going to stick a dual in here. So consider this tensor product of vector spaces transforming in this representation. Now, there's an interesting quantity that I can map this to. The interesting quantity that I can map this to is, let's see. So psi, let's say, is some cast in the some bra in the code space, and then E is some error that transforms in this sub-representation R, and then phi is another vector of the code space. So this is like an inner product. I mean, this is just a number. This is just a complex number. And in fact, it's a very important number. It's the nil-Laflamme error correction condition that we saw earlier. These are the things we've been chasing, the things that we're trying to force to either zero or equal each other. And this is like the things that we've been noticing that they vanish. And now we can just use basically Schur's lemma, a really simple application of Schur's lemma to show that this will vanish under certain conditions. The idea is that this representation over here is transforming in lambda star, tensor R, tensor lambda. We're mapping over here, which is just a one-dimensional space, the space of scalars. So this will either transform in the trivial representation or zero. If there are no copies of the trivial representation in this tensor product of representations, then by Schur's lemma, this entire thing must map to zero. And so that is basically the argument, is you go looking inside of lambda star R lambda for copies of the trivial representation, which you can do by just looking into the product of characters. So this is all being done with, this is looked at as a G representation. That's what we have done, the down. So if this quantity equals zero, then when we look at these nil-Laflamme error correction forms, they have to all go to zero. And therefore, all the errors basically automatically vanish, and we got all these codes for free. And we could just flip these lambdas over to the other side of the character inner product. And so that's how we get the condition that you see, or that's the connection. That's why the fact that UQ is a lambda unitary T group being equivalent to the condition 6, that's why condition 6 has any meaning in terms of Laflamme error correction. It's because it says that a lot of these nil-Laflamme error correction conditions, they're just automatically pushing. Yeah.
Yeah. So this is a condition depending on T. So the very last line, it's for all arguments, they depend. Yeah. As T gets bigger, this condition gets harder.
That gets way harder, and like everything immediately falls apart.
And T is going to be tiny.
T is tiny. T is 1 for almost all cases, and for the icosahedral group, because we got super, super lucky, it's 2. For all we know, the icosahedral group is the only group in the world that you can do this for T equals 2. So this is a cool approach, and it's nice that it's so mathematical, but it's incredibly limited in factual usefulness, as it produces codes that either when T is 1, they have distance 2, or when T is 2, they have distance 3. These are very low distance codes. That's a great question. All right. So, I got excited and already did this whole lemma over here. So that was this slide. I just talked through it. Okay. And so the main result that we get is that if G is a lambda twisted unitary T group, then every subspace of, so this would be like pi 2 tensor n. Oh yeah, down there. Then every subspace of the branch version of apt tensor n that transforms in the irreducible representation lambda in the lambda dimensional quantum code with distance d greater than or equal to t plus 1 and transversal gain group lambda g. So lambda is faithful, then g and lambda and g are kind of the same, but it can be small. Sometimes if lambda is not faithful. And And as you pointed out, yeah, it's for small t, which is the only thing we're doing. It only guarantees you a pretty low distance, which is a very important sort of downside of this approach. And so the way this applies for the binary icosahedral group is that instead of SU2, it's a pi2 bar twisted unitary T group. So every pi2 bar subspace, a pi2 tensor n, it's a two-dimensional quantum code with distance at least 3 and transversal gate group 2i. That n, 7. 7 is the smallest n, such that pi2 tensor n includes at least one copy of pi2 bar. And the reason that the 7-qubit code is unique is because there is exactly one copy of pi2 bar in pi2 tensor 7. Okay. And so now we're going to kind of take a look and see what generalizations we can do and kind of see what we've created here, see how far we've come. And this is really what we do in this paper me and Eric wrote, quantum codes for irreducible products of characters. We do a bunch more examples, and they are all t equals 1, so distance 2 codes, unlike the icosahedral group, which was d equals 3. And the key thing to know here is that there's another way to look at this condition, which is that this condition will be satisfied if and only if the number of irreducible components of F tensor T is the same as the number of irreducible components. It's lambda tensor F down tensor T. So let me just write that up. And then basically, when you work with groups, those equalities on number 2, they're just counting the norm of that, like the number of irreducible components. So basically, the norm of this character F tensor T is the exact quantity, like a little integer that you're going to get on the right-hand side. And so for them to be equal, you need that to be equal to this thing on the left-hand side, which is just lambda F down tensor T. So you're just counting the number of irreducible, yeah.
Yep. So you get those.
Oh, okay. You're just counting the number of irreducible components here, and that's why it's hard to find something that's like, say, a unitary 5 group. Like I said earlier, that 2i is the only unitary 5 group, because this is equivalent to something like this, that basically when you take 2 tensor 5, this is the SU2 representation. When you take 2 tensor 5, it breaks down in some way into SU2 representation. And every single one of those SU2 representations is still irreducible with respect to the action of 2i. And that's pretty remarkable. Because usually when you branch down to find some group, I mean, it all falls apart. Everything goes into spine or fiber grade pieces. Great paper by Graulich and Tiep on small tensor powers. It's published Trail of Algebra or something, where they do this for like all Lie groups and all possible phi systems, finding these really high sort of T design types for some bucket and if not all unitary. Yeah.
Yeah, the comments are question, but I guess the important point about these codes that you concatenate these like concatenated higher level of concatenation still have the transverse getting higher. So that sense, you haven't provided an example of arbitrary distance codes.
Yeah, I suppose that's true. Yeah, I guess one of the things that inspires me about the original codes like 723 is that the transversal gate group 2i is maximal in SU2. And if you start concatenating then I guess the code space can get bigger.
The number of qubits grows.
Yeah, the number of qubits grows, so then right, the distance grows, which is great, but I'm just saying that the size of the transversal gate group relative to the size of the whole unitary group on the
Shows made a lot of qubits. This is like this is what the steam code is used on. Didn't take using concatenation.
Right, but the steam code, right? If you have 2 copies of steam code, then the transversal gate group of the 1413 code, or sorry, 14. Oh, I'm doing direct sum. Am I doing direct sum?
I don't know what you're doing, but it's 40. Yeah, it should be 49.
Oh, okay, yeah. I'm thinking direct sums. There.
Yeah, you wouldn't get the distance to grow with some.
Yeah, that's right. That's right. This would just be a distance tree code again.
That's what in cat these codes that you presented it as a framework.
Yeah.
That you get the property you want, but then that's one construction really just fact you gave them to me.
I gave in to you. Okay, you're on my side. Tell me how great my codes are. Oh, I see like So
Where?
okay, yeah. So here we are. This is actually a slide that I put up, this exact slide 3 years ago during my oral. And I said, there's some cool subgroups of SU2, and it'd be great if I could find quantum codes that had all these in the transversal gates. And so it's just cool to kind of look back and see how far we've come. And I knew that the tetrahedral group you could do with the 513 code. I knew that the octahedral group you could do with the Steen code, the 7-qubit Steen code. But now we have a perfectly good code that implements 2i transversal. So that sort of checks that last box that was sort of on the to-do list from my oral 3 years ago. And here's another code, or another slide is verbatim from my oral 3 years ago. And I said, okay, you can do Qtrit Steen, and that'll allow you to do the Qtrit clip. That is a code that is Qtrit Clipper transversal. But here are some other nice big subgroups of SU3. The second one is a 2 design. The third one is a 3 design. For those who are interested, a 2 design subgroup of SUQ is always irreducible to the agile representation. That's why I have that title. So these are really large subgroups. They're in fact maximal finite subgroups of SU3. And I said, it would be really great to have a quantum code that realized these large and interesting subgroups of SU3 as the transversal gate group. And so that was another goal I set out for myself. And then I did it. So this is like a big old table from this paper, quantum codes from irreducible products of characters. And so being a lambda twisted unitary 1 group is just equivalent to lambda times f down having the same norm as f. And since f is obviously irreducible representation of UQ, being a lambda twisted unitary 1 group, if those what this is 2, this side is going to be 1. So what you need is lambda tensor f to be irreducible. So that's saying that if you have a product of 2 characters that's irreducible, then you automatically get a whole family of these distance 2 codes kind of for free. And so when I'm finding these codes, I'm just saying, okay, I have some group, maybe it's 3.86. And I say 3.86, look at the character table. Are there any pairs of distinct characters that their product is also irreducible? And it turns out that for a lot of interesting groups, you do get this property. And you can, for example, embed one physical Qtrit into 5, or one logical Qtrit into 5 physical Qtrits. And that's sort of the code here. So this is like pretty small. And you can also do, this is a different notation than I used in the previous slide, but this is the simple group order 168 that I was talking about. That's a large subgroup of SU3. And so this is a nice one that allows you to find a code which has distance 2. So I'll just write it up here. Now this is like a code that is a, let's see, we got things we have to be here. So this is 4 7 bits, 4 physical 7 bits that encode 1 less than Qtrit and has distance 2. And this is the code here. So the unitary group on the common space is like U3. The transversal gate group is like this large group of order 168, which is maximal, and it's nice to have as many transversal gates as possible. And using this weird, so this is like perfect group of order 1344. There's 2 of them. One is a semi-direct product. One is not a semi-direct product. They actually have the same character table. You can use either one. And so you can just play these fun games with algebra and get lots of free codes. And that was a really fun kind of ending to our story. We even did the monster group, because there's some useful characters in monster group that have your useful product. And that's, of course, it's not physically reasonable because you're not going to make up this book unit that has like 8 billion levels to it. You could,
How would the distance would be?
check.
A lot of error.
And you shut up. A lot of error is correct. And we do it all somehow. It's all for free. So, yeah. So we were very pleased with all that, and we enjoyed doing all that fun group theory. And we basically called it a day. Thank you.